Hey guys, welcome back to Math from my desk, and in today's video we're going to go over topic 1.3 of the IB Math AA and AI syllabus, which is geometric sequences and series. Before we start the video, I highly recommend that you watch the 1.2 video, which deals with arithmetic and arithmetic sequences and series, because in there I go into detail as to the definitions of sequences and series, and I'm not going to repeat that in this video. Alright, so what are geometric sequences? This is supposed to be a. So a geometric sequence is a sequence where each term is multiplied by a constant value to get the next term. So for example, in this sequence right here, to get from 3 to 6, you multiply by 3. From 6 to 12, you multiply by 2. You multiply by 2 to get from 3 to 6. From 6 to 12, you multiply by 2. From 12 to 24, you multiply by 2 once again. So here, as per the definition, each term is being multiplied by the constant value 2 to get the next term. And if the ratio between consecutive terms is not constant, then this sequence is not geometric. What is the common ratio R? So R is the constant number multiplied to each term to get the next term. So in our previous example, R was 2. Now in this example, which is from 4 to 12 and 12 to 36 and 36 to 108, the common ratio here is going to be 12 over 4, which is equal to 3. So to get from 4 to 12, you have to multiply by 3. From 12 to 36, multiply by 3. And from 36 to 108, you multiply by 3. And to solve for the common ratio here, you simply divide the next term by a term by the term before it. So 12 you divide it by 4, 36 by 12, 108 by 36, and all of these should give you 3. And so once again, this is basically just saying what I in words in writing. So this is the formula for the common ratio. R is equal to U sub n plus 1. So that is the next term divided by the current term. So for example, in a series 6, 3, 1, to get the common ratio, you're going to take the next term, 3, and divide it by the previous term, 3 over 6, which means that the common ratio here is 1/2. And you always want to check at least 3 times before assuming R. So in this example right here, 6 over 3 is 2. 12 over 6 is also 2. But then from 12 to 30, let me go back. But then from 12 to 30, it is no longer 2. So you always want to check at least 3 times before being able to confirm what your R is. And you want to do this unless the problem in the question specifies that the sequence is geometric. Otherwise, you'd just be wasting precious time if you do this check. Types of geometric sequences. So if the common ratio R is greater than 1, that means that the sequence is increasing. So the terms are going up. If the common ratio is between 0 and 1, then this sequence is decreasing. And if the common ratio is less than 0, so if it is negative, that means that the sequence is alternating, meaning that you go from -2 to a positive number, then to a negative number, etc., etc. This is the nth term formula. So this is how you can find any term in a geometric sequence. U sub n is equal to U sub 1, the first term, multiplied by R, which is the common ratio, to the power of n minus 1. And this is in the formula booklet, so you do not have to memorize it. So for example, we have a geometric sequence with terms 2, 6, 18, and it goes on. The first term here, U1 is 2. The common ratio is 3 because 6 over 2 is 3. And so is 18 over 6. All right, now if we want to find the sixth term, we simply apply the formula. We have U sub 1, 2, times R, 3, to the power of n minus 1. So to the power of 6 minus 1, which is 5. And this ends up rendering 486 as an answer. Now we move on to geometric series. So a geometric series is the sum of the terms in a geometric sequence. And this is the formula for the sum of the first n terms. So it's a big and complicated formula. Note that there's 2 equations you could use, either this or this. They're practically the same. And this is in the formula booklet, so you do not need to memorize it once again. So for example, here, the sequence 3, 6, 12, etc. U1 is equal to 3, so that's the first term. R is equal to 2, since 6 over 3 is 2, and 12 over 6 is also 2. And n, for the sake of this problem, let's say it is equal to 5. Then if you want to find the sum of the first 5 terms, you apply the formula that was shown before, and you end up obtaining 93. Sigma notation, so once again, this was covered in the previous video, but sigma notation is essentially a compact way of writing the sum of the terms of a sequence, and the symbol sigma simply means to add up. So this image explains it better. So below the sigma sign, you have the value of n, so that is where you start summing, and then at the top is where you stop summing, and here is what you end up summing. So for example, here we have the sum from n equals 1 to 6 of 4 times 2 to the n minus 1. So see here that this follows the nth term formula, so this is u sub n. And here you're adding the first 6 terms, so you go from n equals 1 to n equals 6. So for the IB, you have to be familiar with this notation, and you also have to recognize this sigma notation always represents a series, not a sequence. And you also have to be able to identify key elements from an expression with sigma notation. So for example, in the previous example, you have to be able to identify what U1 is and what R is, for example. Real-life applications of geometric sequences and series. So these are the examples which the IB lists. So population growth, if a population increases by a fixed percentage each year, then that could be modeled as in a geometric way. Same thing for the spread of diseases, whereas each infected person infects multiple others. And depreciation value, so an asset loses a fixed percentage of its value each year. And in the IB, you may very well be given geometric sequences and series problems within real-world contexts like population growth and spread of disease. All right, as I mentioned before, I will soon be making a video on how to use a graph and display calculator for sequences and series, so stay tuned for that. All right, now the TOK part. So for this subsection, the IB gives us the question, how do mathematicians reconcile the fact that some conclusions seem to conflict with our intuitions? Consider, for instance, that a finite area can be bounded by an infinite perimeter. So you might want to think about this. This seems like a fun thought. And here I have attached a screenshot from when I asked DeepSeek this question, so you may want to read that. All right, thank you guys so much for watching. Please like and subscribe, and I'll see you soon for another video.